right, in today's lesson, we're going to be looking at several friction examples that involve sliding, tipping, and then a scenario where we don't know what's happening. And so we're going to show how you set up the principles, how do we draw the free body diagrams, and how do we get the information that we need to be able to use a logical conclusion to determine what scenario happens first. It's kind of applications of the logic, and it is an extension of our previous video. I hope it meets with your approval. So without further ado, here we go. Okay, and so this is a fairly classic kind of problem. Okay, and what I have here is I have a weight, a mass of 20 kilogram weight. It has a height of 0.6 meters. It has a width of 0.8 meters. And then I'm going to apply this force at an angle of 30 degrees to a point on the side of the block such that it is half the height. It's 0.2 meters up. Okay, and we know that the frictional value between mu s, the frictional value is 0.3. The mu s is 0.3 occurs at the interface between the bottom of the block and whatever the surface is. Okay. All right, so all we do is we go through and we draw our free body diagram. Clearly the object can't move down because of the ground pushing up on it, but there is a horizontal component of this guy that's wanting to move the block to the right. So that's why my F we're drawing goes back to the left. All right, and then as it goes to the left, then my normal, if you look at the horizontal with P and the horizontal with F, it wants to cause a rotation that's going in the clockwise direction. So to counter it, the normal wants to move back to the right in order to produce a moment with the weight in the amount shown that is acting in the counterclockwise direction. Again, this p-value, or sorry, this weight and this normal form a couple that wants to fight the horizontal of this and the friction value. Okay, all right, so in our picture here, we have basically three unknowns, right? I've got the F that I don't know, I've got the N naught that I do, well, I can find it based off of these forces that I know. And then I've got this unknown position value. Those are the three unknowns. And three unknowns on a single free body diagram is solvable. I can do, write my three equations, sum of forces X, sum of forces Y in the moment. I can start to work with this. All right, so let's work through this fairly quickly once we get this thing set up. Okay, so the weight is going to be mass times gravity. 20 kilograms times 9.81 meters per second squared gets us 196.2 newtons. That's the force that's there. Okay, and then all I'm going to do is I'm going to go in and I'm going to write my three equations. Valid free body diagram, this is always the next step. Go write your equations. All right, so for our picture that we have, okay, if I sum forces in the x, and I'm going to say to the right is positive, then we're going to take the x component of this p force, that's 80 times the cosine of 30. To the right, that's a positive, and then the F is acting back to the left, that's a negative. Equilibrium occurs when all that is equal to 0. So to maintain equilibrium on this, F was found to be 69.3 newtons. Okay, that's what's required to maintain this in equilibrium. Now, we don't know if the object is sliding yet or not. Okay, we've got to go figure out what that limit is, if you will. And the way that we get to that is we're now going to go in and we're going to look at our Fy value, okay, for sum of forces in the y direction. And we'll do that by taking the y component of my p force. So that's an 80 newtons times the sine of 30, and its component is acting down. So that's why it's a negative, plus the normal NC value that we don't know, okay, minus the weight of the block, this minus 196.2, okay, and all that has to be equal to 0. So if you do the math, this normal is 236 newtons, okay? All right, now, we need to figure out, well, what's the position of this x? Okay, where is this force at? Okay, so again, my tipping point will be here. Okay, but we're going to measure x off of the line with the weight. Okay, so if I do that, we're going to sum moments at what we're calling as point O. That's the point that's here, directly below the weight. And I do that to knock the weight out of this picture, okay, and to also get me a valid representation of what this x dimension is. Okay, so if I do this, then the moment about O is going to be, we're doing 80 sine 30, so we're going to take the vertical component of this guy, okay, multiplied by 0.4 meters. So that's 80 sine 30 times 0.4, and that's wanting to go in the counterclockwise direction, and I'm assuming counterclockwise positive here, so that's no surprise, okay? And then because I broke it into components and I accounted for the vertical, I also have to account for the horizontal, okay? And so that guy is going to be an 80 cosine 30, okay? And that horizontal piece creates a moment multiplied by 0.2, by taking that force and multiplying it by 0.2 meters. Okay, and this one wants to rotate the guy in the opposite direction. He's going in a clockwise direction, so that's why it's a minus here. Okay, and then with this, I can go in and say, okay, the weight doesn't contribute because it's acting through the point, and so the moment that NC makes in, it's just NC times X. And based on our picture, that's counterclockwise, that's a positive, and so that's our equation. All that equals 0. So what happens is these forces, if I go and I solve for X, then you actually find out that X is negative, right? So what we thought was originally this normal wanting to drift this way to create that couple is actually going the opposite. And the reason for that is that the horizontal of P was to the right and F was to the left. My couple for that was clockwise. But I also build in this angled force acting down on this relative to O that is creating a counterclockwise moment. So he's actually, he's actually wanting to help turn this object over. So it's actually, in order to counterbalance that, it's going to pull our force negative. So what's really happening on this picture is my normal is here. It's actually going to end up being just a hair over here. Okay, now the amount that it moved based on X was 9.08 millimeters. Okay, well, we know that we were at 0.4 meters for this horizontal distance, so 9.08 millimeters is left of O, but is less than 0.4 meters. So we know that it's still in contact with the block. This object is not tipping, all right? And so that becomes the logic portion. So since X is less than that B over 2, because again, that's B divided by 2 is that value. Okay, no tipping occurs. Okay, so we know no tipping hasn't occurred, but we don't know whether or not the object is sliding. Okay, and the way that we figure out if it's sliding is we go back and we calculate what that limit was, this F max. So F max we said was going to be the static coefficient multiplied by that normal. So if I take my coefficient of 0.3 and I multiply it by the 236 NC value that we saw, we get a force of 70.8 newtons. Okay, and so for us, the horizontal component of that force P, or our piece of X piece, in order to make this slide, must be greater than 70.8 newtons. If we hit 71, I've exceeded the limit. This thing's going to break free and start to slide on its own. Okay, and once we get it. Now, for us, since our F that we found from statics, was in the amount of 69.3 newtons, okay, that's less than this F max. So F for equilibrium, if you want to put an EQ on there, we can. So the equilibrium force that maintains equilibrium from the statics equations is 69.3, and the maximum before movement occurs is 70.8. So this guy is less than this, so that means that there's no sliding either. This object is still in equilibrium, and it hasn't moved yet. Now notice it's getting really, really close, and a little bit more force, and this thing's going to start to slide. Okay, so, and that's kind of the nature of the basic friction calculations that we can start to look at. But you can start to see how we can start to set up some logic for this, okay? So we're always checking. If you want to make kind of a list on this, you're going to check for sliding, okay, and we're going to check for tipping, okay? Because the trick on this is that both of these are forms of motion. All right, so on a test, maybe you're asked to find the force that causes motion. Okay, and if that's the case, if they don't specify sliding or tipping or which case they want you to calculate for, then you have to figure out which one is the controlling factor. In this case, sliding is the controlling factor. Okay, and then you have to be able to determine, but these are the two approaches. So if you look, all we did was we solved for X for the tipping case, so that told us it wasn't tipping, and then I turned around and I checked the sliding by checking the forces to make sure that this equilibrium force was less than that limit, that F max value. Okay, and so that kind of becomes our basic approach. So, all right, so that will conclude our basics introduction for friction. In our next video, we'll look at some examples and some actual applications of mechanical apparatus that include those things like wedges and belt friction, and friction on how it applies to pulleys will all be coming up in future examples. So as always, if you would, if you've got any suggestions for improvement or things that we can do to make this a little bit better, or information that you want to see more of, just leave us some feedback down below in the comment section. As always, like and subscribe to the channel, and we'll keep the videos coming. So hope you all have a great evening. Happy engineering. All right, our next example is a fairly classic example out of physics, but we'll kind of walk you through the process and hopefully show you some other ways to kind of start to look at things. All right, what we have here is we have a ramp that is oriented at some particular angle theta, which is an unknown in this case. And we have an object that has dimensions of 8 inches tall by 4 inches wide and has a weight of 20 pounds. All right, we're given that the coefficient of static friction between the bottom of the object and the top of the ramp is a value of 0.55, and what we want to find is what's the largest angle theta that can occur before the block starts to move. Okay, now as you start to analyze this problem, as we've talked about previously, there are different mechanisms at work here. We could be sliding, we could be tipping, and since we don't know which occurs first, we have to check all of them. Okay, and one of the tips that you see, on a typical undergraduate level statics class or even a physics class is that sometimes they're a little bit vague, and this word right here, moves, doesn't say anything about which of the cases it is. So anything is fair game. All right, so always watch the wording of the problem. That's kind of your pro tip for the day. All right, so as always, first thing we're going to do is we're going to look at what our free body diagram looks like. We're going to take a look at what is the impending motion direction. So this object, clearly, if it has a weight that's acting at the center and acting down on this, then I have a component that's acting this way, and I have a component that's acting this way. That means that the impending motion is acting in that direction. All right, and so if that's the case, then that means that we automatically know that if that's impending motion, then friction has to be opposite to that. All right, and so that's what we're going to draw. So here's our graphic, or free body diagram, if you will. And so what we've done is I've drawn the object. Okay, and again, we have dimensions of 4 inches and 8 inches tall, so I know that this dimension is 2 inches, and then we have the 4 inches labeled from the bottom of the object up to here, and that helps us to triangulate to where this center point or the centroid of the object is. Now again, we're assuming that that's the point where the weight is acting, that everything is uniformly distributed. There's no one side of the object doesn't weigh more than the other, whatever the case may be. So that's how we come up with centroid. If it were one of the other cases, then you would have to go figure out using your centroid calculations where that centroid would be. But since this is a rectangle and we're just looking at a simple example, we'll assume that's at the center and we'll be good with that. Okay, so that's our self weight. Now again, remember, kind of as a recall, we're doing Y's, all right, which is weight, internal forces, support reactions, external. So kind of for the weight, I is internal. The only internals that show up will be what's happening at this interface when I pull the block off the ramp. And so we talked about impending motion being down the ramp. So friction, and if I call the bottom of this thing B, friction at B will be acting up the ramp. Okay, and then we have the normal, and trying to figure out where the normal is on this. Looking at these forces, this thing wants to form a couple. The vertical or the horizontal component of the weight in conjunction with this force causes a counterclockwise rotational effect on this. So that means that this normal has to move over here in order to counterbalance the vertical component of this guy. All right, so this normal will cause a counter rotation in a clockwise direction, which will help to hopefully hold it up. Okay, and then again, the unknown that we have in this picture is this x that is measured from, in this case, the centroid line, okay, perpendicular to n. So it's this dimension right here. That's our x. Okay, now one of the tricks that we do on this example to kind of help solve or simplify our math is that we're going to take our coordinate system and we're going to orient it just a little bit differently than we normally do. All right, I'm going to align x with the ramp angle. So if we put this on here, we're going to align x with the angle theta, and then y would be perpendicular to the ramp. And what that does is that will greatly simplify my equations, and we'll show you those here. What happens. So once we have a valid free body diagram figured out, now we can go in and start drawing our equations of equilibrium. Okay, and so what we're going to do is, now I'm going to kind of violate our sign convention a little bit, and it doesn't matter what direction you assume positive. I just assume down the ramp positive, and I'm going to sum forces in the x direction equal to 0 relative to this new coordinate system that we have happening over here. All right, so what happens is that FB becomes a negative value because I assume down and to the left was positive. All right, so FB is acting up and to the right. That's a negative. That gets me that. And then I have the component of this weight, that are relative to that system. So here was, and this is the one part that's a little bit tricky on here. So there's my weight. Okay, I get a weight in the x direction this way, and I get a weight in the y direction that way. Okay, and then this would end up being my angle theta also. And so these will be the components that we have to work with. So I have to split this guy up, but I know his value, so it's not a big deal. Okay, and so when I do that, that's going to be then, so Wx is the sine of theta multiplied by 20 pounds, and his component is acting in what I called as a positive direction. Okay, according to my sign convention here. Okay, all right, so now for the y direction, we do the same basic game. I'm going to take my NB, that's this guy, okay, and he's acting in what I assume to be positive, up and to the left positive, so it's a positive NB, and then I'm going to subtract off this y component, and so the y is going to be 20 pounds times the cosine of that angle, and so that's the equation that I have here. All that's equal to 0. Okay, all right, and so that gets us a couple of expressions, and I can see that once I find an expression for FB, I can get theta, or once I find the normal, I can get theta, so on and so forth. All right. Now, the other piece that we have to check or establish now is the moment equation, right? Because again, a valid free body diagram requires all three: forces X, forces Y, and moment. Okay. Now, where you take the moment doesn't really matter. I know the last time we took it at this point, you could take it at the tipping point. For just to be a little different, I'm going to choose to take it at the top of the NB load, because by taking the moment here, what will happen is I will knock NB out of the equation. And since I don't know NB, because as we saw up in this equation, it's a function of theta, by summing moments here, I eliminate it out of the picture. Okay, and so that could prove to be a little bit useful for us. All right, so all we're going to do then is the only force that's acting on this is the weight in his component. So I'm going to take the Wx times 4 inches, and I'm going to take the Wy multiplied by its dimension of what would be x. All right, so if we look at it, I have my Wx was that 20 sine theta term again, and since it's acting, down and to the left, that wants to cause a counterclockwise rotation about O. That's why it will be. Okay. All right, sorry about that. Just noticed I had, for the equation that I had written, I had taken the direction of the moment in a different way. All right, so as we were saying, this guy right here is my Wx, and this guy right here is my Wy. All right, so Wx we said was acting down and to the left, and so that wants to go counterclockwise. So we kind of call that, now notice I've switched this in order just to make my equation right. It doesn't matter which way you assume, the signs are all relative to that. All right, so this will be positive in the clockwise direction for once. So it's going to be a negative times Wx times the 4-inch dimension from here to here. Okay, plus then our Wy, which is our 20 times the cosine of that angle theta, and it's going relative to this point. He's acting down that way, so that's going to want to go in the clockwise direction around O. So that's why it's a positive, and then its distance is going to be x. And so that's our equation. All right, so just for the sake of argument, what we've done, if you're playing along at home, I'm going to call the first one equation 1, second one equation 2, third one equation 3. All right, and then we'll start to see what we can do with the parts for that. All right, okay, so what we're going to do is we're going to basically go in and check our impending motion calculations. All right, so what we're going to define then is that the Fs, that we know that Fs max, okay, is going to be equal to mu times n for the static coefficient. We talked about that in the last video. All right, so then my maximum FB value for sliding to occur is going to be mu, which was 0.55 multiplied by that normal. Okay, and we will call that then as equation 4. So we're building up a lot of equations in order to be able to solve for stuff. So all I'm going to do is do a bunch of algebra and substitute this guy in for FB, and then we'll just be able to solve for, in this case, we're going to take the fourth equation that's here. Let's go to characteristics, take our fourth equation, plug it into the first. All right, that's my FB for equilibrium, into the first equation, solve for FB max, and then turn around and take that guy, and we're going to plug, once I have FB max, I can find NB, and then NB can plug into here, and then with that, I should be able to come up with an angle for theta. All right, and if I do that, and I go through the algebra, again, that's just an algebra exercise, the information that shows up on this for sliding to occur would be that theta equals 28, Sorry about that. Let's get that down there where you can see it. Okay, the theta is 28.8 degrees. Okay, FB is 9.64 pounds. And then the NB is equal to 17.5 pounds. That's just an algebra exercise to solve those four equations for each other. Okay, all right. And so then once I know theta, I can plug theta into my third equation, which was that moment equation, and I can solve for what x is. All right, and so what we're going to find then is that x, in order to have this object start to slide, ends up being 2.2 inches. Now this is greater than our b over 2, which was 4 inches over 2, or 2 inches. Okay, therefore, tipping occurs first. All right, and so now we know that it doesn't slide first like we had assumed, and we had assumed that back up here when we made this FB max, you know, equal to our FB. Okay, so we assumed sliding was happening on that one first. Okay, so we know then that you know, because x is greater than 2.2 inches, which is greater than 2, we just showed that, okay, that our normal force on the free body diagram is actually somewhere out beyond that tipping point. Okay, which means that for us, tipping will occur first, will occur before sliding. All right, so that means then we got to check tipping. Okay, now what happens in this picture then is the point at which it tips is the point that corresponds to this normal being located at this tipping point. So that's the outermost value, it's the largest value of x that I can get to before this force leaves the object. Okay, so we know then that for tipping, as we're saying here, okay. Here. Let's get this position where we can see stuff. Sorry about that. Okay, for us then, we're going to check tipping. X is equal to 2 inches. Okay, that's the maximum that it can be. So this is the tipping case. And then all I do is I plug back in to those equations that we had up before. So if you look, if I know x, I can solve for theta. And then once I know theta, I can get NB. And then once I get theta, I can also get FB corresponding to it. All right, so if I do that, then the set of data that comes out of that then is that theta for tipping occurred at 26.6 degrees. And then FB is 8.94 pounds and NB is 17.9 pounds. Okay, and so what we look at then is that we can kind of do a quick check on this, is that, you know, when we check our FBs for the friction values, this was the guy that we had set equal to FB max, right? That was the sliding criterion, you know, using the logic that we've established. Okay, and what we found is that this guy from before was an amount of 9.64 pounds for sliding. Okay, this guy now we just said is 8.94 pounds, so it's clearly less. All right, so this object never slides; it never reaches that maximum limit before it starts to tip. Okay, so then the angle at which motion starts to occur on this then is an angle of 26.6 degrees. That's the first one. So what we're doing is we're assuming that we're taking and we're starting out at a horizontal, and then we're basically increasing theta, you know, up to whatever, to some angle, and until it does something. You know, in this case, it tips first, and then if we're able to go a little bit further without tipping, it would then start to slide down the object. And that's part of the function of that static coefficient as well. All right. All right, our next example is a little bit different. Okay, what we have is we have a system that consists of a simply supported beam in which it's pinned at A, and the NB is sitting on top of a block wedge. All right, and we have a uniform load acting on our beam of 200 newtons per meter. The beam is 4 meters long. Okay, and then this block is now sitting on the surface, so it's just kind of pushing down and wedging on itself. Okay, what we're going to do is we're going to apply a force at a location of 0.25 meters above the bottom. Okay, the whole height of this is 1 meter, so we're going to pull it out from the bottom. We want to find out what's the force for P in order to be able to break this block free and be able to pull the assembly out. Okay, so we're after finding P. Okay. All right, now, so what we're going to do is we're going to go in and kind of draw a free body diagram, as you might expect. Okay, and it turns out there are two of them that we have to draw, right? There's one for each object. Okay, and so here are the pictures that we're going to look at. So what I have is I have my simply supported beam. So I've got an AY and an AX. Okay, I've taken this uniform load as outlined by this dotted line here, and I've turned it into an equivalent 800 newtons, which is the 200 newton per meter times the 4 meter length as the resultant of that distributed load, and it's located at the middle of that load pattern, or at 2 meters from the end. Okay, the support conditions that are happening here is I have the vertical reaction, which is the normal at B, okay, but I also end up with, a frictional value at that interface. Now, I don't necessarily know the direction of this until I go down and I look at the block below. So here's the free body diagram of the block below. All right, so at the top I have an NB acting down. That will be coming from the force of the beam above. Okay, my impending motion direction of this thing is this way. So that's my impending motion. Okay, and so if impending motion is to the right, we said friction always opposes it, acting back. So we have an FB back to the left. I have an FC at the bottom, back to the left, and then I have the support reaction from N acting up. So once I have these two established, then I can go up and I can do the opposite on the beam up above. So that's how I knew FB was acting to the right. It's not entirely intuitive. So you got to look at the piece that's actually moving when you start to draw the free body diagrams associated with this. Now, we're going to be given that the static coefficient at B is 0.2 and the static coefficient at C is 0.5. All right. So what you might expect is we start writing equations. So the place where I often start with these is I start with the force and work on the object that has the force that I'm after on these. All right. So all I'm going to do is write my forces X, forces Y, and my moments. Okay. And so if I do that, then I'm going to have, P to the right positive minus FB, okay, minus FC, all equal to 0. So that's one equation. All right. So we're going to call that as equation 1. Okay. For the Y direction, all we have, and what we've done is we've neglected the weight of the block, so there's not a lot there. Okay, and so for this picture here, it's NC up positive. I have minus NB acting down. Okay, and we know that NB, because this is simply supported, that NB is 400 newtons. It's half of the 8 that was here. And then AY is also 400 newtons. So I know if it's up 400 here, it's 400 down here. So that's where this minus 400 is happening there. Okay, and so that one I can solve, and it tells me that NC is 400 pounds. So again, we've assumed that this is a weightless block. There's nothing on there. If that's not the case, I could just as easily add a weight in, and we could factor that in. But for this exercise, we're going to leave that out. Okay, the last equation that I'm going to write then involves coming in and figuring out what's the value of P in order to make this object move. So for equilibrium, I chose to some moments at the bottom of the block. All right, so if I go counterclockwise positive, then it's a minus P times 0.25 meters. So that's a minus, and that's a positive. Okay, and then plus FB times 1 meter, and all that equals 0. So that's the third equation that we have. All right, okay, now here's the thing. Because these friction forces have different coefficients on there, I don't know which one occurs first. Okay, and so what will happen is that motion on this thing, in order for this thing to move, is I have to basically break or exceed the frictional limits at both locations. Now the problem is I don't know which one is going to go first. All right, so the two cases that exist are that FB, and again, remember this equation is equal to mu times NB, that's FB max. Okay, that if FB reaches its limit, that end will pull out, and then I don't care what FC is at. All right, so that's why we've got some inequality around here. So I'm going to set this equal to the maximum for B, okay, and then FC can be either less than or equal to that NC value multiplied by the static coefficient. Okay, or it could be the other way around where C reaches the limit first, and then I don't care about FB. As long as I break 1, this thing will pull out. All right, so we're going to take this one. FC is equal to mu C NC. So again, this is FC max. Okay, and then that means then that FB is going to be either less than or equal to mu B times NB. Because again, I can't exceed this. If this ever exceeded that quantity, I would be back up in the first case. So it's one of these two cases has to be true. Okay, now the problem is we don't know which. Okay, and so that's what we're going to work on next. All right. Okay, so since we don't know which, we're just going to guess. We're going to choose one and then test it. So again, this was FB max. Okay, and then my criteria is that FC is less than its max value. All right, so to get FB max, that's this. On here, I'm going to take 0.2. I'm going to multiply it by 400 newtons because that's the mu. That gives me an 80 Newton FB value for FB max. Okay, and so all we do is we basically go back into our moment equation, and I solve for the FB value, or plug in the FB value, and solve for the P that would cause FB to be equal to that value. Okay, so if I plug in 80 newtons for FB, multiply it by the 1, and I play with my signs, again, this is a minus, and that was a positive for our equation. That's fine. We find out that P is equal to 320 newtons on this particular object. So in order to break it B first, P would be 320 newtons. Okay. If I go through and I check the calculations on this, I can go back and I can look at that sum of forces in the x direction. On there, P minus FB minus FC equals 0. So I have my 320, which is the P that I just found, minus the 80, which was my FB max, tells me that FC has to be 240 newtons. Okay. At that particular instance. So what we have to look at is we now need to check if FC is greater than FC max. Okay, because if it is, then we're in the wrong case and we've overestimated the load. So that's all I'm going to do. So let's check FC max real quick. Okay, we're going to take mu C times NC, so that's a 0.5 times the 400 newtons. That was the NC normal force. It tells me that this is 200 newtons. So now we're saying that FC is greater than FC max, which is violating that assumption. Okay, because so again, we made an assumption of both of these things having to be true. Now this one is true, but that one isn't. So this means that this case is not a valid case, right? So it means that the slipping will occur at C first, not at B. So it's the other criteria. So now we go in and basically we work through the example in much the same fashion. All right, so FC then is mu C times NC. Okay, so again, that's FC max. Okay, and then FB is less than or equal to the FB max value. This is the case that has to control. So when I do that, we find out that FC max is 0.5 times 4. That's the 200 that we saw. Okay, and then if I plug back into those equations, you can find out, doing the exact same step as what we did in the previous step, that P corresponds to 267 newtons and FB is equal to 66.7 newtons. Okay, so the P from this case is 267, all right, as opposed to the 320 that we got previously. So for that reason, as soon as I hit 267, the bottom of that block will start to slide. Okay, and then I'll be able to pull it out. So 267 newtons is my limiting load, and that will cause the bar to be removed, or that block to be removed. Okay, now, kind of some extra tips that we might want to kind of keep in the back of our mind as we're solving different types of friction problems. Okay, for friction problems, you must determine which location fails first. And by fail, I mean which one exceeds the sliding limit or exceeds that frictional limit. You know, F equal to F max. Okay, and whenever you have these scenarios with multiple cases at work, you know, to start with, all you do is you guess one of the locations is going to fail first, like we did here. Okay, and then basically go back through the process and verify your answer. This is the important part, right? Because if I would have just done that first calculation like we did here with the 320, I would have well overestimated the actual load that it would take to pull that block out. All right. So I hope with these, it gives you kind of a sense of what you can do and some of the different types of problems that can start to show up when you're dealing with friction. So we've done, a pretty simple sliding problem in this video. We've done, a tipping or sliding problem that was unknown, and then we've got something that's a little bit more complex that involved multiple locations in which only one of them had to fail. So, like I say, I hope this gives you a little bit of an idea of what you can see happening on a quiz or an exam in a statics class with regards to friction. So anyway, I hope this all made sense. As always, if you leave some comments down below, if there's anything that we can do to improve the videos or improve the exercises, we would love to hear that feedback. As always, take a second and subscribe to the channel. Like us if you wouldn't mind, and we will see you next time. Happy engineering.